Hello, I'm Professor Mark Porosov, and I'm going to tell you a little bit about my group and our research into development of catalysts for CO2 hydrogenation. So my group currently consists of 3 PhD students, Mitch, Renji, and Jane, and 4 undergraduates, Connor, Ahmed, Daniel, and Sam. You can see us on the left here in a recent socially distanced group gathering. And so this image is an infrared satellite image of the Earth, where in the dark red, we can see high concentrations of carbon dioxide. And I like this figure because it's a good representation of the classic chemical engineering equation, input minus output plus generation equals accumulation. And we see the red here represents high concentrations of CO2, which are accumulating in the atmosphere in the northern hemisphere winter. And to reduce the atmospheric concentration of carbon dioxide, we really need a combined approach of increased efficiency, cleaner energy, carbon sequestration, and what we focus on, CO2 conversion to chemicals and fuels. So there are applications of this happening now, where in Iceland, they have a process to sequester CO2 within basalt rock, so the reverse of cement production. Another example in Iceland is CO2 conversion to methanol, where they have a plant driven by geothermal energy that can produce up to 5 million liters of methanol per year. Out in Western Canada, there's a company, Carbon Engineering, that's capturing CO2 for fuels direct from air. And finally, a kind of out there application is on Mars. There's interest in storing hydrogen within CO2 as methane for return missions to Earth. And if we look at the reactions that are behind many of these reactions we just discussed, they're all listed here, where we really focus on first looking at the thermodynamics, where we see methanation is strongly thermodynamically favorable, and CO2 Fischer-Tropsch to make chemicals and fuels is less favorable than methanation, whereas reverse water gas shift and methanol synthesis are less favorable reactions. So what we like to do in my group is to use kinetics to produce CO, which can be used as a precursor for valuable olefins and heavier hydrocarbons for fuel, and also try to couple these two reactions into one pathway where we can start with CO2 and form chemicals and fuels without producing methane, which is already abundant in the US and is a waste of valuable hydrogen. So we like to focus on ethylene and propylene, light olefins, because they're important raw materials for manufacturing plastics, chemicals, and fuels. And ethylene and propylene are the top 2 produced petrochemicals worldwide, right now produced from steam cracking of hydrocarbons, like large hydrocarbons like naphtha, or methanol to olefins. So what we'd like to do is develop novel routes to make light olefins out of carbon dioxide. And so as an example, on the left here, if we use traditional catalysts, generally they're subject to this Anderson-Schultz-Flory distribution, which is a polymerization model for producing hydrocarbons from CO2. And that results in very wide product distributions and low selectivities to the desirable olefins. So we're looking at 2 different routes, one through a CO intermediate and one through a methanol intermediate, over 2 distinct catalysts within one material, so a tandem catalyst, to directly produce olefins from CO2. So we need this multifunctional catalyst, and we've achieved some success already at this first step of the reaction using a potassium-modified molybdenum carbide catalyst. And actually, our recent publication in Energy and Environmental Science, our potassium-modified molybdenum carbide catalyst has among the top performance of other catalysts in literature for the reverse water gas shift reaction, which is CO2 plus hydrogen goes to CO and water. So we see, if we consider both the CO production rate, so how fast we make CO2, and the cost of the CO2 on an active metal basis, our catalyst is closest to the top right corner, meaning that it is both the top performer when we consider production rate and cost. We're also looking at ways of making these tandem catalysts through core shell materials, where we take a core material, in this case it's iron supported on ZSM-5, we surround it in more ZSM-5, and we have evidence here both in the increased CO2 uptake, the higher BET surface area, and the shift of this temperature program desorption curve to higher temperatures, that we're successfully encapsulating these iron nanoparticles within ZSM-5, which is very exciting for being able to develop a tandem pathway where CO2 can react over the iron, and then it can react further over this zeolite as it diffuses out before it can exit the reactor. So that's really a general overview of what's going on in my group. If you'd like more information, please feel free to contact me by email. My email address is listed here, and I'd be happy to answer any additional questions that you have. Thank you very much for your time and attention, and look forward to interacting with you in the future.